In this video, we're going to look at the binomial theorem and proof of the binomial theorem. And we're also going to examine the general binomial theorem and some special cases for it. And I'll explain why when we get there. So this is the this is the binomial theorem, where n is a non-negative integer. We're going to prove this by induction. So we're going to first show that it's true for n equal 1, and it is. So if you raise it to the 1, make n 1, it is true. So now, next we assume that it's true for n. So we assume this is true, and then we need to show that that also means it's true for n plus 1. So we go about that. Here is the first piece, raised to the n plus 1, and we can separate that into the product of x plus 1 to the n times x plus 1. And then we expand this, we know this is true, so we put that in here. And this is y raised to the k, my ink got a little bit sloppy there, times x plus 1, which is this piece. Now we're going to take this times x and then add it to this times y. So one of these x's goes in here and raises this exponent to k plus 1. And that's what this is. So the negative goes in, so it's minus k plus 1, but I'm going to write it like this. And then here the y goes into here, raising it to k plus 1. Okay, so now we want to separate this. This goes from 0 to n, but let's take out the 0 piece and then sum it from 1 to n. And we're going to, so we take out the bottom piece here. Here we're going to take out the top, the n, and then we're going to sum it from 0 to n minus 1. So that's what we do here. This is the when k equals 0 piece, and then this is the k1 to n piece, and this is the k to the n minus 1, and this is the nth piece. Now here we're going to, in this piece we're going to do an index change. So the k is sort of a dummy variable. It really doesn't matter what it is called. So we're going to call it j, but we're going to let j equal k minus 1, which means k is j plus 1. So this piece is this, and then when we substitute in k, so here k, it's j plus 1, that's what is here. And then k is j plus 1, so one of the ones cancel, so we just get n minus j. And then these are the same. I take off the coefficient 1 here. So now each of these terms goes from 0 to n minus 1, 0 to n minus 1. So I combine these and just have one sum. So this piece comes down, this piece comes down, and then the x's are the same. So from 0 to n minus 1, from 0 to n minus 1. So these combine, the y's combine, but we have an n, combinations n choose j plus 1, and then this would be a n choose j. So I want to have a little side note how to deal with this addition of combinations here. So a side note, we're going to look at this here and just expand this by definition, expand this by definition. Now here we have to find like terms. So if we take out a j plus 1 here, okay, so here what we do is this factorial comes down, and then this is j factorial times j plus 1. Okay, little ink mess up there. Here the j plus 1 comes down, but we take out one of these. So it's n minus j times n minus j minus 1 factorial. So this is separated here. So these two pieces are the same. So we need to multiply this over here and this piece over here. And that's what we do here. So then we get the like denominator of j plus 1 factorial n minus j factorial. And then that's the multiplication we talked about. But if we factor out an n factorial, that leaves n minus j plus 1, and the j's cancel, leaving an n plus 1. But this right here is just n plus 1 factorial. Now the denominator, we keep it the same. And then here, if we add 1 and subtract 1, then we get the same. But then this makes it easier to see that this is the n plus 1, choose j plus 1. So here, we're going to replace it with this. And that's what we do. Okay. So now I want an index change again. So we're going to I'm going to call it k again, but which is a different k that we used up here. We're going to let k be j plus 1, this piece here. So then that means, we're going to let k be this, and that means j is k minus 1. So when we put in a j here, then we get k minus a minus 1, which is a plus 1. So actually, let me show you that. So this becomes this. The j plus 1 is just k. There's no j or k here, so it comes down. The k is j plus 1. And instead of going from 0 to n minus 1, we go from 1 to n. Okay? But this formula here, when k is 0, it actually reduces to this. So we could take this piece and put it in here and go from k equals 0 to n. But if we were to go from 0 to n plus 1, we would actually grab this piece too. So, which is this. So we go from k equals 0 to n plus 1 of this, and that's what we needed to show that the binomial theorem is true. Okay, so here the general binomial theorem. And one of the reasons I'm doing this is early on in my career, going through a proof, they would write something down and they would just say, hey, due to the binomial theorem, this is true. And it never seemed like it was, it wasn't the binomial theorem that I was referencing. And so, I had to look it up and understand it. And they were referencing the general binomial theorem, which is, it's the binomial theorem, but the n can be any real number r. And it can be written in a very similar form to the binomial theorem. The binomial theorem is a special case of the general binomial theorem when n or r is n, a positive integer. So here, I wrote it in this terms where this is what's called a falling factorial, and I'll explain that in a second. Otherwise, it's the same. And then you can trick this into looking like a combinatorics, r choose k, but it'd be more explicit here, falling factorial. So a side note, this is what's called a falling factorial. It's in parentheses r sub k, often written r superscript a with an underline under the k, which means you're falling. It's r falling factorial. So you start out with r, whatever real number, you just subtract 1, subtract 2, and you keep going until you have k terms. And that's called a falling factorial. Well, then you might think, well, is there a rising factorial? And the answer is yes. It's usually written as this or this notation, where it's an r superscript and the underline is above the k, meaning it's a rising factorial. And it's just the opposite. You start at R, and you go plus 1, plus 2, until you get k terms. That's called a rising factorial. Now here are a few cases that I want to examine. And the reason is that in later videos, when I say due to the binomial theorem, but I'm going to try to always say general binomial theorem and then refer back to this video, is when we have 1 plus x to the half, it can be written as an expansion. And these are so easy to prove just by Taylor's expansion. So easy to prove, but I'm not going to do it here. Or if it's to the 1/2, you get this. If it's to the minus 1, which is 1 over x plus 1, which is this. And then also if there's a minus n, so it's 1 over 1 plus x to the n, which ends up being this. And what's kind of interesting here is you have n and then n plus 1, and then each term is an n plus 1, n plus 2, and then so forth. So that's a rising factorial. So it can be generally written as this, where you have a rising factorial over factorial raised to the k plus 1. Anyway, so these are the general cases or specific cases of the general binomial that over the next few months that I'm going to reference, saying, hey, due to the general binomial theorem, this relationship holds. Anyway, I hope you enjoyed it. If you did, like the video, subscribe so you don't miss the next video. Bye-bye.